Hi everyone, my name is Jordan Shen. I'm presenting our work, Fast Video Object Segmentation using the Global Context module. This is a work during my internship at the Applied Research Center of Tencent's PCG, and it's a collaboration with my colleagues Dr. Yu Li and Dr. Ying Shan. Today I'm going to first present some background knowledge about the task of semi-supervised video object segmentation, and then I will introduce the space-time memory module, which was the previous state of art on this task in detail, because this is the work that we are basing our global context module on. And then I will go ahead and introduce our global context module, including how it works and how it solves the major pain point when we apply the STM module in practice. After that, I'm going to present empirical results on 3 different datasets and finish this presentation with a discussion on the potential future directions for this research. The task of semi-supervised video object segmentation is like this. You're given the video sequence and then an object mask on the first frame, and your task is to propagate or generalize this mask onto the remaining frames. The deep learning approaches to this problem can be categorized into 2 major schools: online learning methods and offline learning methods. Online learning methods are produce quite satisfactory accuracy, but are slow because you have to do training during inference. Offline learning methods, in contrast, are faster but also less accurate. It can be further divided into template matching methods, which uses the first frame as a template, and mask propagation methods, which propagates a mask from the previous frame. However, both of these approaches have their own drawbacks. If you use the first frame as a template, then if the object's appearance changes over time significantly, then it will be harder and harder to produce high quality segmentation in the later part of the video. If you use the last or the previous frame as a reference, then the problem will be the previous frame's segmentation result is also the prediction of the model. And if you make any mistakes on the previous frame, it will be carried over to this frame and then onwards. Because both of these frames have their own drawbacks, there are some hybrid methods proposed to combine these 2 approaches and mitigate both of the drawbacks. Along this line, the most successful and the most elegant approach is the space-time memory module. Basically, the space-time memory module says that instead of thinking about whether to use the first frame or the previous frame or some other frame to guide the segmentation of the current frame, why not just use all of them? And to do that, they generate a pair of feature maps, the keys as the memory indices and the values as the memory content for each frame. And then for each frame in the memory, and then for the current frame. You also use a different encoder to generate a key feature map and the value feature map. And then you use the current frame's keys and the memory content and to put them into an attention mechanism and generate memory readings, which encodes the information stored in the previous frames that are helpful to the segmentation of the current frame. Finally, you concatenate current frame's value onto it, and then which generates the final output of the STM module. The problem of this approach is that you have to keep a pair of feature maps at each passed frame, which means that the more frames you have processed, the more memory you will use, and the more computational load you will have. And if you have a long video, and then this module will get slower and slower, which will eventually defeat the purpose of the STM module, which is to use all past frames to guide the segmentation of the current frame, because the high costs will force you to once again only select a few frames to guide segmentation of the current frame instead of using all of them. Therefore, when we design the global context module, we aim to solve this pain point of the STM module in a fundamental and principled way. Our core our core observation is that the STM module can be written into this matrix equation, and with some basic linear algebra manipulations, you can rewrite this equation into this form. And this equation actually has some very interesting properties, which I will not dive into in details due to time limitations. But instead, let's focus more on the visual depiction. So basically, the first equation in the previous slide corresponds to the STM module, and the second one corresponds to this illustration. And as you can see, the main difference between the STM module and this new approach is that after obtaining the keys and values at each pass frame, you send them into a further process and generate the frame context, which is a global summarization of this frame. And then you add up all these frame contexts to form the fully spatial temporally global context feature of all pass frames. Then, when you want to get information from the memory, you don't need to do the the heavyweight attention process with all these feature maps, but instead you just directly index this global context with the current frame's keys to generate the distributed global context, which is basically equivalent to the memory reading in the STM module. This, at the first sight, this might look quite different from the STM module, but in practice, actually, the two equations, which was shown on 2 frames ago, are actually equivalent to each other, which guarantees that this global context module is almost mathematically equivalent to the STM module, except for that if you do some normalization, for example, apply a softmax function inside the STM module, it cannot be fully replicated in this new formulation. But that is the only place that these two modules are not mathematically equivalent, and later we'll show that in practice that does not hamper performance at all. So this table gives a comparison between the efficiency, both in terms of memory and computation, of the GC module and the STM module. And you can see that in both memory and computation, the GC module is substantially more efficient. And it's more efficient not only with respect to the temporal duration of the video, but also with respect to the spatial resolution of the video. So now let's dive into the experimental results and see how the GC module performs in practice. On Davis 2016, you can see that the GC module achieves almost the best performance among all the online or offline methods, and at the same time also achieves the real-time processing speed. So the end result is that it's quite clearly in the top right corner in this graph, which shows how well it handles the trade-off between speed and accuracy. On Davis 2017, the situation is basically similar. On YouTube Voice, GC is still among the best approaches, except that the STM module outperforms it by quite a bit. But after some further investigation, we found that the main reason of the performance gap between these two models are not the models themselves, but different testing protocols. If we apply the same standard testing protocol to the STM model, we'll see that the performance gap basically disappears. So for future directions, I want to especially stress that the GC module is not designed towards any specific feature of the task of video object segmentation. Therefore, it should be generically useful for any video task that requires temporal context or temporal alignment. Thank you for watching my presentation, and if you have any questions, you're welcome to our discussion sessions to discuss.